Thank you. First of all, let me thank the organizers for putting together this very nice event and for inviting me here. I'm enjoying really much the program and learned a lot in this week. So, the work I'm going to present is, yes, as Robert told, is getting back to hydrodynamics with some special kind of initial conditions. So this work, first let me just introduce my collaborators. So the works I'm going to talk about was done in collaboration with Matthias Gruber, Florian Meislinger, and Hans-Gerd Ewerts from the Technical University of Graz. So let's start with a brief introduction to the problem. So what I will be interested in is hydrodynamic behavior in integrable systems. But instead of trying to sort of go into different understanding, I would try to apply, so basically the simplest form of the generalized hydrodynamics, which we have learned this week. I would like to try to apply this to a specific setup, which I'm interested in, and it has to do with domain walls. This is called the geometric quench, which I will introduce. One of the main my main interest in the problem is actually also from the perspective of entanglement evolution, since this problem will be seen to have, so the initial state is actually in the language of beta ansatz will correspond to a zero entropy density state, which means that the standard particle picture for the entanglement evolution, which predicts the linear growth of entanglement, as we have seen in various previous talks, will not apply here. So actually this situation will be pretty different from this picture, and this is also sort of an attempt to understand these situations where the entanglement growth is not linear, but it's sublinear. Okay? So this will be sort of the first part of the talk, and in the second part of my talk, I will consider a completely different setting. It will be still a domain wall, but the main question is, okay, up to this point we have heard several talks about GHD, how to set up the problem, and we have seen the ways how you can calculate, for example, the densities of the conserved charges, or how you can calculate the currents of these charges. We learned it from Balázs. Or Benjamin taught us how to calculate the expectation values, well, correlation functions, essentially, of local operators. But assume we have an operator which is, for example, the density of some non-conserved quantity. What is even worse, it could be some completely non-local object. For example, you don't have to go very far to find something like this. Just think of the sigma x magnetization, the order parameter in the Ising chain. It's, in terms of the fermionic variables, it's a string, so it's a highly non-local object. The question is, and the corresponding charge, if you integrate the full magnetization along the x direction, it's a non-conserved quantity. So even though the system is an integrable system, but you are interested in a quantity which has a non-trivial description in terms of charge densities, if you wish. So the question is, what happens in this case? Is there still some description? Unfortunately, I'm not going to answer this question because it's too difficult in general, but I will try to do some case study in specific cases, namely the XY chain, and try to show you a couple of examples what kind of behavior could emerge. Then I would also talk about some examples of non-analytic behavior, starting from a domain wall initial condition in this context. It turns out that if you vary your Hamiltonian, time evolution Hamiltonian, you could tune the system through a point where the profiles you observe go through some kind of interesting non-analytic behavior. And finally, I will also ask the question whether there are some universal regimes in the time-evolved profiles which can be identified and described. Okay, so let me give a brief outline. So, as I told you in the first part, I will be interested in a GHD description of geometric quench, and I will apply this for the XXZ chain, and I will study magnetization and entanglement profiles. In the second part, I will be interested in a completely different type of domain wall in the XY chain, and I will show you that hydrodynamic phase transitions could occur. Then I will present the results of some form factor calculations for these specific type of domain walls, and show you how a hydrodynamic behavior could emerge also in this case. And I will also discuss a bit the edge behavior. So these are essentially results taken from several papers, some of them still unpublished. So let's start with this slide. Unfortunately, I don't have to spend too much time because we have seen this a couple of times. So basically, generalized hydrodynamics is a very, very nice description of integrable dynamics. The reference is, as we have seen. So basically, what we have is a system with infinitely conserved charges, and essentially, you can interpret this system of continuity equations as an infinite system of continuity equations for all the rapidities. I took this picture from the paper of Elijah, Ben, and Takato. This is one of the problems you could be interested in. This is called a bipartitioning initial condition. You take something homogeneous on the left, homogeneous initial state on the right, and let the system evolve, and then you get some structure where sort of you get a local quasi-stationary state depending on the ray parameter. So everything will depend, since there is no intrinsic scale in the problem, everything will depend on this ray variable, which is just the location from the junction divided by time, okay? So this is a picture of two different temperatures. I will be interested in a different setup, but still it will be also a partitioning protocol if you wish. Okay, so the tricky part about these continuity equations is essentially these velocities here, which are the Dresd velocities, which makes the problem much more complicated than of course, the free Fermion case, where these velocities do not depend on the state itself. But of course, for the XXZ, we have interactions, and that's why it's much more difficult to arrive to a complete analytic treatment of the problem, because at some point you have to invoke the TBA, the thermodynamic beta ansatz machinery, to get these velocities, okay? So let me introduce the problem, the so-called geometric quench. So this problem has actually been, the name has been introduced by Mossil, Palacios, and co. In this paper, and the very same setup actually was treated already by Vincenzo and Fabian Heinrich Meissner in 2014. But as you see, this was still the pre-GHD era. So essentially, although the setup they considered is exactly the same what we did, but they mostly concentrated on the non-interacting problem, because there was no kind of machinery to get the profiles for the XXZ case. So I decided, since this is one of the simplest setup you could come up with, I decided it's worth of re-investigating it with the techniques of GHD. So as you see, the initial state I'm preparing is a bipartitioned case, but instead of the domain wall, which you would typically think of is spins up and spins down, this is now instead the ground state, the half-filled ground state, or zero magnetization ground state, if you wish, connected to the fully polarized vacuum state. Okay, so it's the ground state plus the vacuum. It's still some sort of a domain wall because the magnetization has a jump in the middle, and I will be interested in the time evolution. The nice thing is that the ground state has a very, very simple description in terms of thermodynamic beta ansatz, since this is given by the solution, the root density is given by the solution of these integral equations. And essentially, if you think about the particle, the filling factors, so the densities of particles divided by the total densities, since the structure of the ground state is just a completely filled Fermi sea, if you wish. But you have to fill all the rapidities between minus infinity and infinity. So essentially, this is, in the rapidity language, this is the simplest object which can be called a domain wall because you have fillings 1 on the left and fillings 0 on the right, okay? So if you were to consider the standard domain wall, spins up and spins down, there you already have to fill 2 families of quasi-particles, which makes the problem, in a sense, more complicated. In a sense, it's easier because, as some people in the audience showed it can be solved analytically, but the behavior will be very non-continuous in delta, okay? On the contrary, in my case, in the geometric quench case, these are the real rapidities, so they always exist and they don't change as you change. You can take whatever delta parameter you wish, and this is a continuous problem, okay? So after this motivation, let me come to the solution. So as it was shown in the very first papers of GHD, if you have a partitioned initial state, then the solution of the continuity equations is very simple. Essentially, you have a piecewise homogeneous solution for the filling factors. Yes? I will consider an infinite line. Actually, in the beginning, so the initial state is like, you can think of it as 2 half-infinite lines, and you join them. Of course, in our DMRG simulations, we take a finite system, but you don't go. Yes, but this appears in all kinds of these problems. You always sort of assume that you can apply the machinery of TBA to this problem. You don't care about boundaries, sort of. It's present in all of the treatment of GHD, actually. I agree, there might be issues, but these are typically have to do with boundaries, so you might neglect some Friedel oscillations or sort of these things, but it turns out that the machinery works perfectly. So you can apply the standard thermodynamic beta ansatz description even though you have a boundary. Okay? Yes, exactly, because for large times, the interesting part is deep in the bulk. It's not, because particles are coming, going, and it's always what in the t goes to infinity limit is always the bulk which is interesting, and this is captured by TBA. Okay? Any more questions? All right. So this is this piecewise homogeneous solution, which gives you essentially, the answer is that you have particles which can, so for a given ray parameter, in my case, as I showed on the previous slide, the left filling is just 1, the right filling is just 0, so you will have only this term here, and this will tell you that the filling is just determined by the particles by the particles with having effective velocities larger than the given ray parameter. Okay, so the particles that could already have arrived at this position will determine the filling at this point. Okay, so now there is one tricky issue when you go from this description. So this thing still contains the velocity. You would like to give an ansatz in terms of the rapidity itself, like this. So that rapidity is larger than a given than a given value lambda star appear. But for this, you have to assume actually that this rest velocity is a monotonous function. Okay, so only in that case you can rewrite this equation into this equation. And this is what we assumed in the beginning, but it turns out that for the xxz, it's not true. It's only true if you consider attractive interactions, which are these dashed lines. And as you see, if, as long as you go to the positive repulsive interactions, there is a clear maximum in the curves. So it means that you have to be careful, and your filling function can be defined the usual way, like just rapidity is filled larger than a given lambda star. But in the general case, for positive interactions, it turns out that the bare velocity has a non-trivial maximum for this rapidity parameter, which actually has always value 1. Okay? So for delta larger than 0, you have always a bare velocity at a certain value of the rapidity parameter, which is equal to 1. Okay? On the contrary, for negative interactions, this maximum goes to sine gamma, okay, which is always smaller than 1. So let's see what it means for the densities. These are the plots of the profiles, of the magnetization profiles for various delta parameters. The blue curves are the MRG simulations. The red curves are the solutions of the GHD ansatz. Either this one or this one, depending on the value of delta. And the interesting thing is that there is two completely different behavior emerging for positive and negative delta. For positive delta, actually, I mean, if you first look at the curves, they don't seem that much different, but then you can have a look at the details. First of all, if you look at the edge, at the right edge, so this is the vacuum edge, this, actually, there is a simple calculation you could do. It's very similar in spirit to the one Jean-Marie presented. And what you find is that actually the profile for any values of delta to the lowest order approximation is always a square root. Okay? So it's a square root singularity around the edge. On the contrary, so this edge, as I told you, is always at 1, and the ray parameter 1 because of the maximum in the velocity. On the other hand, for negative delta, you find that there is a separation between the GHD and the so-called free magnon edges. So this is very, very similar to the domain wall, so the real up, spin down domain wall problem, which has been studied by many people in the audience. And Jean-Marie's talk, you could already have a glimpse of roughly what is happening. So there is somehow, the GHD predicts, roughly physically what you can think of is that there are attractive interactions. This renormalizes somehow the velocities, but still at the end of the front, there are some particles which might escape, okay? So the attractions are not, they are strong in the bulk, but at the regime where the particles are still dilute, they don't yet feel this bulk renormalization effect, so they can just escape. And they just propagate with the free magnon velocity. And if you magnify this region, then what you find here is this is the edge. This is the GHD edge, but there is a clear fat tail which emerges. However, if you scale everything according to the zeta parameter, you can see that it slowly decays. And as Jean-Marie told us about, it's might be that if you integrate the number of particles, it's still something which is a non-regular logarithmically growing function. In any case, what one still expects that in the really, if you go into the scaling limit very large times, then this tail slowly disappears. Okay? Yes? For positive delta, you don't have to come up with any argument because there is no separation. The maximum velocity is 1, which is the Magnum velocity. So there the interactions are repulsive, so they tend to increase the speed, but apparently due to this maximum in the bare velocity, this just agrees with the free Magnum velocity. So there is no separation, and as you see, the GHD prediction, well, basically, if you don't magnify the curve for all of these curves, you see that there are very nice agreement between the GHD and the DMRG. But there are these issues for attractive interactions, and for attractive interactions, there are other issues actually on the other end, which look even more wild. This is harder to comprehend in terms of, but this must be, again, some effect beyond GHD, so these are some particles which escape from the bulk. Okay, so, and on the left-hand side, the velocity for any positive and negative interactions is given by the spin-on velocity, since this is propagation in a zero magnetization background, okay? So this does not depend on delta, this velocity, apart from, of course, these extra features which we don't understand. Good. So this is a very nice proof that GHD works very well for such problems. But now let's come one step further and let's see what we can say about the entanglement profiles. And this is roughly the picture you get. So these are now, again, the same delta parameters. And now the curves correspond to different times. So this part on the left is just the ground state value, because the front, the propagating GHD front has not yet reached this part. So if you cut your system at this position, you will just measure the ground state entanglement. But as you go inside the front, there is some non-trivial profile emerging. This has already been, at least if you cut in the middle, this has been studied already by Vincenzo and Fabian Heinrich-Meissner, and they already saw that the time, the growth in time is described by logarithm, okay? So it's not a linear increase of entanglement, but some logarithmic increase. So now the problem is that whenever you want to apply particle picture to entanglement, it will only give you linear growth, okay? It's no way to, at least no one has yet described anything which is logarithmic in terms of quasi-particles, at least the qualitative structure. Of course, quantitatively, you can see very nicely that these edges here correspond to the spin-on velocity, to the left, to the maximum right velocity, just as for the magnetization. So qualitatively, you see that this front region in the entropy is there, it's described, but if you want to get the full thing, the full profile, it's not so easy. Again, there is some difference if you compare, for example, the positive and negative delta case. I forgot to mention for the domain wall, so the up-down domain wall, the simple domain wall, this is a symmetric problem. So if you take plus or minus delta, there is a dynamical symmetry, which is not present in our case, okay? So there, in that case, these profiles would just look the same. Now we compare the entanglement profiles for, I think this is plus and minus 0.8, the delta, and you can see that for the plus 8, the profile in the entanglement is much sharper. Somehow you can you have a soft versus a hard edge in the entanglement. So these tail effects are also present there. Okay. But of course, one would like to get some more detailed description, and this is not so easy to give, even for the simplest case of a local quench, and actually all the cases where the growth is logarithmic, you must go back to CFT. Okay, so there is no quasi-particle picture which would give you a quantitative description of these profiles. No problem. Let's see what we can extract from CFT. So there are different results. The local quench I refer to is if you connect two chains. So now I will only consider the XX case as from reasons that will become clear in a moment. So this is only for the non-interacting case that we can give a quantitative ansatz, actually, conjecture, which seems to work very well. So if you connect two chains which have the same density, 1/2, so there is no bias, no kind of domain wall, then Pasquale and John Cardy found in 2007 from CFT considerations a nice formula for the entanglement profile. Now it was extended by Jérôme and Jean-Marie in 2011 for the case of finite systems. So if you don't connect to half-infinite, but to finite systems, you just have to change the variables with the chord length variables, and you get the result. Now, so actually, maybe what I forgot to give you first is the idea. So basically, what we want to do is, so these are the free fermion velocities. It's just a sine function. So what we would like to have is, in the semi-classical or hydrodynamic picture, what you do is just you choose a ray parameter, zeta, and you count the particles. For example, if you want to get the density, you count how many particles could reach this zeta. This is just the portion of the velocity which is larger than this zeta. Okay. So if you took the domain wall quench, then you have this full interval. Okay. But now in our case, the situation is different because, of course, these are fillings which are higher than pi/2. So half filling means that you don't have particles which have, in the initial state, these states are unpopulated. So you have to cut this here, and you have only 1/2 of them. Okay? So there is a sharp Fermi edge, if you wish, at pi/2. And that was which led us to think about that somehow these problems, so the domain wall, local quench, and the geometric quench should be somehow related, at least in this simple XX case. So the idea is the following. Now, in this case, for the geometric quench, you have sort of the combination of the two effects. So for every ray parameter, you have a filling, local filling, which varies for the domain wall quench. Here, you have the same, but at the very same time, you have a sharp edge, which is always there. So this sharp edge is reminiscent to the local quench case. But now, in the local quench, you actually have both edges at -pi/2 and +pi/2. Okay, this sort of corresponding to two front velocities to the left and to the right. So if you separate Jean-Marie and Jérôme's result in this way, then you can see that this is an additive description of a left and right propagating front. Okay, so now my trick is that I would like to take only the right propagating one, but at the same time, I somehow have to sort out also the contribution from the ray-dependent entanglement. And this can be done in the following way. For the domain wall quench, actually there is an answer. What is this? So we considered this problem in 2011 and found a function which describes, but actually we found it only numerically. But then in 2017, Jérôme, Jean-Marie, Jacopo, and Pasquale came up with a beautiful description of the problem. Essentially, you can understand the problem as sort of a CFT in a curved background. So you have to consider a curved metric for the CFT. And once you are able to transform the problem back to the homogeneous problem, you know what kind of transformations you have to do, and you apply the standard twist field approaches Olaja introduced us, you get the answer. And the answer is the following. It has two parts. There is a universal part, which is described by this variable. This pops out from the conformal transformation, by which you first homogenize the curved space, and then you map it to the upper half plane. But then there is a tricky part, which is related to the cutoff Olaja already talked about, which you always have to put in somehow by hand in a CFT. So this cutoff in the homogeneous problem, it's well known that it's related to the density, okay? So because that's somehow the only relevant scale which is present. So apart from now, what I'm going to think of is, instead of having these amount of particles, now I have actually only exactly 1/2 of them. So what I'm going to do is just half, yes? Why? This one? So in the domain wall case, you have in the initial state each momentum mode is field. So you just have to find the ones at the ray parameter zeta which are larger than whose velocity is larger than zeta, okay? So this is this interval. But if you consider geometric quench, which has a half filling, then you don't have modes larger than pi/2. Those are missing from the initial state. But somehow you have a symmetry in the problem, and that's why I can only actually treat this 1/2 and 0 densities, because here you can argue that there is a particle hole symmetry in the problem, and if I considered these guys, they would give the same contribution, at least as far as the universal part is taken into account. But other than that, I have to change the renormalization, which is due to the density, which is again 1/2 of the domain wall problem, since you have to take only 1/2 of the particles, okay? If you put all these things together, then you arrive to this ansatz, and it turns out that it really nicely agrees with the simulations for the XX case, okay? Yes? This is, so R is the distance from the middle, okay? So this is like such a bipartition. R counts the distance from the middle. So your result is R equals 0. Yeah. Indeed, indeed. So I was back then puzzled by this result, but I could not decipher it. But now we came up with this conjecture, which seems to work very well. Other questions? So then, yeah. No. We only considered really this partitioning protocol. That could be, yes. Yeah. Yeah, that's an interesting idea. No, we only consider the piecewise homogeneous filling. Okay, so let me go to the second part now, which is a completely different setup. As I mentioned already in the beginning, now I will work with the domain wall, which is in a non-conserved charge density, okay? So in the XXZ case, I was considering the magnetization, the integral of which is always conserved by the dynamics, so everything works out fine. But if I consider, let's say, an XY chain, which is the textbook example of a spin chain, a free fermion integrable spin chain, then it's well known that there is a ordered phase, and there, actually in finite volume, there is always two almost degenerate states with zero magnetization, but in infinite volume, you can always consider the symmetry broken ground state, okay, where you really have an ordering. So this is sort of a linear combination of two vacua, which is usually the Neveu-Schwarz and Raon sector. And these are the following examples which I will consider as excitations. So how should I now create the domain wall? Well, it's very simple. I just flip the spins up to a certain point with the sigma z operator, okay? The ordering is always in the x direction, because that's the stronger direction. So when I want to create a domain wall-like state, then I flip everything with sigma z, and then I put, just in case, I put a sigma x at the end. I have a very good reason to do that, because I want to consider a local excitation in terms of the fermions, okay? And this is, of course, just the string variable, which is the Majorana fermion, okay? So this is perfectly local in terms of fermions. Now, I could also do something more general, is a double domain wall. It's a very similar construction, but now I don't take the full string. I just cut it off from left and right with the sigma x. This will flip all the spins between n1 and n2. And essentially, you can rewrite it again as it's not anymore a single particle, but it's a two-particle excitation in terms of fermions. Okay. And the most funny thing, the most funny situation will be the single spin flip, which can again be written as a two-particle excitation. In XXZ language, if you create a single spin flip excitation, you don't expect anything non-trivial to happen. You would expect that it just disperses. But here, since this is a non-conserved quantity, so you flip sigma x spin, you will see that it's a highly non-trivial profile which emerges, okay? Yes, and of course, I have to say that actually here, I don't really do any quench. So I prepare this ground state of my Hamiltonian, and then apply some excitation on it, but then I evolve with the same Hamiltonian. I don't change my Hamiltonian, okay? I just prepare some non-trivial initial state. So let's see what's happening. First of all, the reasonable object to consider is the normalized magnetization, because the ground state magnetization, it depends always on the parameters of the starting parameters you choose in the ordered phase. But this guy, if you normalize it by the ground state magnetization, will always be between -1 and 1, okay? Of course, if you want to study this problem, analytically, it's not so simple, because you have to consider form factors of the magnetization. I won't show you the details, but essentially what you have to do, you rewrite the initial state in terms of the eigenstates of the Hamiltonian, and then you have a double sum, and you have to consider these single particle form factors, so 1 + 1 particle form factors, and you have to do the sum, of course, or integral in the thermodynamic limit. It's not so simple, but actually, if you are interested in sort of the hydrodynamic limit, then the only thing what you have to do is the stationary phase calculation, okay? This will give you the scaling limit, where you keep x over t constant, okay? So let's see. I will put immediately the result here. This is going to be given by an integral 1 minus 2 times this integral, where this theta is the step function. So again, you see the same result emerging. So you just have to count the particles. Now you have to think about each of these particles as carrying a single spin flip, the density of a single spin flip, okay? So all of these particles, put them all together, that at time t0, they put together this spin, this domain wall. The time evolution, each of them carries a single spin flip, okay, the density of it. So you just have to add them all together, and you see these are plus or minus ones. So if it's a plus one, then it turns the magnetization to 1 minus 2 times 1. So this really corresponds to a spin flip. So if I consider this very simple initial condition, it turns out that the hydrodynamic formula emerges as we wish. Okay. Now let's see what else could happen. So this is a nice effect which we termed hydrodynamical phase transitions. Since if you look at the dispersion relation, it turns out that so XY model you fix some gamma and now vary the magnetic field H. Turns out that at some point, HC equals 1 minus gamma square, your dispersion relation changes from a 1 minimum to a double minimum structure. In terms of the single particle velocities, this means essentially you can, for small q's, you can give this approximation for the dispersion, and you see that essentially this is sort of the mass of the particle. If you go below HC, it turns out that there's a negative mass appearing, right? So if you plot the single particle velocities, you go to negative q's, which you would say is momenta, negative momenta, but still they have positive velocities, okay? So in the end, you will have, if you, for example, consider here a ray parameter which is smaller than this maximum, then you will have two branches contributing to this integral. And this is how this extra kink appears in the profiles, okay? So the green curve corresponds just to the critical point where there is a vertical slope of the profile. If you go below this critical field, then there is a kink appearing. So this is sort of analogous to some kind of phase transition also because of this negative mass description. But importantly, it really only appears in the dynamics. There is an interesting analogy because this phenomenon, or at least not this phenomenon, but this critical value was found by Tomáš Prózon and István Pizsorn in 2008 for boundary-driven open systems. So for closed time evolution, I'm not aware of any results where this particular H parameter would play any kind of role, but this was found in boundary-driven open systems, but there the mechanism is different because there you see a transition in the steady state, okay? So depending on whether you are above or below this field, you get a different steady state for your model. Here, actually, you just see these kinks in the hydrodynamic profile, but if you wait long enough time, so the steady state, of course, always means that you have to be here in the middle, roughly. This always converges to the real ground state, non-magnetized ground state in our case. Yes? Sorry, if you... Yes? Yes, this is exactly what I wanted to point out here. This is the point where you get the second branch, yes. All right? So in our case, we cannot really claim that we know what is the NES, but most of the indications, so if you look at the entanglement entropy, for example, you see that the growth of the entanglement entropy is exactly log 2. So it indicates that somehow you get from the symmetry broken ground state to the real ground state of the model. So this domain wall just flows out and you recover the non-magnetized ground state. So there we know that this HC does not play any role. If I had the square root of this is the factorizing field, which has some role in the phase diagram, but this field in the ground state, there is no specific role to this field. So this is really a hydrodynamic phase transition. Absolutely, absolutely. This, where the kink appears, is just this velocity. This is the maximum velocity. The second maximum gives you the kink position. The factorizing line, this is, you should take the square root. That's a different, usually I also mix them up, but this is really two different things. So in the ground state, nothing really happens. Okay, let's see what's going on for the double domain wall. How much time do I have? 10 minutes? 10 minutes. All right, perfect. So if you consider a double domain wall, and I will consider only the case where these guys are well separated, okay? So I don't want to bring them close together, but two domain walls which are well separated. And then I do the time evolution. So the initial state now, as I pointed out, it's now given by two particle excitations. So you see that your task is becoming more and more difficult, because now you have to consider, I did not dare to put the expression of these form factors here. Already the 1 plus 1 form factor is still quite simple. There is one feature you have to be aware of. There is a pole. So if P equals to Q, there is a pole. So actually that's what gives you the particle. The incoming wave P and the outgoing wave Q, they have to match. This is what gives you a particle contribution. So it turns out that if you do the stationary phase calculation, which is now a bit more complicated because you have a quadruple integral, but it turns out that the result is very simple. Actually, the only contribution is now for both domain walls, for both kinks, you have a bunch of incoming and a bunch of outgoing momenta, but the only contribution is if you match those two guys, okay? So the incoming momenta at the left domain wall have to go into the outgoing momenta of the left, and similarly to the right. So the second kink in the second domain wall. And this gives you a factorized formula in this form, and this is still a semi-classical or hydrodynamical, if you wish, interpretation, because again, these are just plus and minus ones. You just have to, if there is a location that a particle could arrive from both initial kinks, initial domain walls, then they both turn the magnetization at this location, so you have to add a plus one instead of a minus one, okay? And then you have to add up over all the possible momenta. Okay, so this is a completely standard semi-classical result. So we are happy, again, somehow, even though that we don't have a priori arguments that for this density, for this variable, the GHD machinery works, but due to the form factor calculation, it turns out that it gives the right answer. But now let's come to the last case, which will be the most tricky, is the single spin flip. So essentially, here, the initial state has two components. There is a component with the vacuum and two particle excitations. But now, as I told you, here, the single spin flip could be thought of as a double domain wall, which are just next to each other, okay? So these are basically, if you create one kink, but right away you create another kink, then you will get just a single spin flip. And this is how you have to interpret this evolution. Because this single spin flip will not just disperse, but it will give rise to a highly non-trivial profile, which is, again, a finite thing if you plot it against the ray variable. Okay? So you see that this is a absolutely non-conserved thing. You start with a single spin flip, and you have a ballistically extending profile, so the sigma x magnetization grows and grows and grows. Okay? And this is because you have to think of this as a double domain wall problem instead of a single spin flip. Okay? But now, if you do the calculations, what you can identify is the following. There is, okay, so the magnetization has three contributions. There is something coming from the vacuum expectation value. Then there is the result which we had for the double domain wall if they are well separated, which is the standard semi-classical one. But now I have an additional contribution, which is sort of an interference effect. So the incoming momenta from the first defect could scatter into the outgoing momentum of the second defect, because they are very close. They are next to each other. So you can have an interference effect that one of the incoming momentum goes into the outgoing momentum of the second domain wall, okay? And it turns out that it has a contribution which looks almost semi-classical, but you have to include phases, okay? So you have to include the Bogoliubov phases here, and you get something. So this expression is complex, and then you have to take the absolute square. So this is really looks like an interference effect, and this is not present for the well-separated domain walls, okay? I don't know. Honestly, I don't want to make a conclusion that this is differing from hydrodynamics, because I don't exactly know what GHD would tell me for this quantity. So it might, yes? No. These are the profiles. So these are really... the other thing is that this is really not just a correction. So if you had only this result, in the middle, this would give 0, because that would be symmetric. But you see, this goes down to minus 0.4. So this contribution is really non-negligible. This has the same order of magnitude as the semi-classical one. I don't know the interpretation, but this is certainly what you get from the form factor calculation, which is the real thing, if you wish. So I'm still puzzled how to interpret this and whether this is reconcilable with GHD or not. Okay? And my final slide is about the edge scaling. Namely, if you consider the domain wall, then it turns out that if you are looking at the edge of the profile, then you have to do a bit more complicated stationary phase calculations. And it turns out that there is another scaling regime, which we have heard already in Jean-Marie's, which is described by a different sort of function. Or, well, you could think of this rho function as the approximation of this integral, right? So instead of the theta function, or the integral over the theta function, you have now a non-trivial rho of x, which is given by a well-known object. This is the airy kernel, or more precisely, the diagonal part of the airy kernel. Now, if you go to the spin flip case, it turns out that it's still the airy kernel, but there is some non-trivial prefactor, which depends on the Z magnetization, okay? So we are looking at the sigma X magnetization, but still the prefactor of the airy kernel, or the diagonal airy kernel part, gets a non-trivial prefactor, which depends on the sigma Z magnetization, okay? All right, so, but apart from this, it looks like that the scaling works very well. So you can really recover this, this non-trivial prefactor, which you obtained from the stationary phase calculations. All right, so with this, I would like to conclude. Actually, what I wanted to transmit you in this talk was that the GHD, if you apply it to a very specific and very simple problem, can perform perfectly, and we can find non-trivial behavior, first of all, for the difference between positive and negative delta, so attractive and repulsive regimes. Of course, there are still different things to understand, like this non-trivial edge behavior Jean-Marie already talked about. And then the other thing was about domain was in the XY, where in certain situations you get an emergent hydrodynamic behavior, and then for other situations you get some interference effects, which is not yet clear how to interpret. Of course, a long-range goal would be to understand how one could generally treat such problems where you have a density which is non-local or not even conserved. But this is, of course, it's a far apart goal. So with this, I would like to thank you for your attention.
Yeah, just a comment to say, actually, I have general formulas from GHD for